All right, first of all, hello everyone. Also, thank you for coming out here and listen to me on a Saturday. Also thanks for the intro. Didn't know I was that well known. My name is Alex. I work as a solutions architect at AWS. And today I'm going to show you the GPU orchestration playbook for AI inference at scale, which essentially, over the next 40 minutes, we are going to look at how you would go and run AI inference at scale, meaning it's not only you running Olama on your workbook, on your notebook and having like one model, it's rather like a higher number of users and you have probably hundreds or thousands of GPUs. Bringing me to the question, who here is actually doing this? Who has hundreds or thousands of GPUs running probably right now? One person, nice. All right, so you are paying dinner, right? Because the first challenge we have with AI inference at scale is that GPUs are A, expensive, and B, it's hard to get them. Probably no matter where you actually run. Also, the workloads are, let's say, special. And also, I think I put it in the abstract, but this is obviously running on Kubernetes, and it's not originally built for this. So in the session, we're going to dive into how we can make this a bit easier. But first of all, why is inference hard? And I see 3 points here. The first one being that it's stateful, and it's like mighty stateful. It's not, it's even a bit more different than if you would run databases on Kubernetes, which is also a thing these days. This is even harder because, like it says on the slides, the model weights live in GPU memory. So if you would spin up a web server pod or a pod for some web application, it's probably snap of a finger and the application runs. Good to go. With AI or with AI inference, you first have to load the model weights. And it's not like snap of a finger and you're good to go. And depending on how you do this, you will have a problem with the third challenge that I'm coming to. But the second one is that you have very variable load. And now you might be thinking, yeah, that's like with every workload. However, with a traditional web application, you would have something like all your requests most likely look the same. They cause the same the same load in the end. But with AI inference, you might have big prompts, medium prompts, small prompts. So the load caused by individual requests really varies. And then what also will vary is the latency that the answer of your model will have. And this makes it really hard to do good capacity planning. And last but not least, kind of connects to the model weights or to the statefulness. You have really slow cold starts, not only with your container images, but it might also be that your cold starts, that your nodes have cold starts, depending on how you actually build your nodes and how you actually build your system to scale. And so saying something like, oh yeah, I'm just going to spin up a new node and I can handle more load, probably not going to happen unless you're prepared. So these are some, let's say, fundamental engineering challenges that we have to solve. However, who knows the 2 different phases that AI inference is actually made up of? We have the pros. Okay, so he already knows, because the root cause of some of these challenges here is that AI inference is actually made up of 2 phases with different needs. The first one is prefill. This is essentially taking all the tokens from your prompt and then computing everything, computing all of them in parallel. So it crunches through all the tokens and then puts them in the KV cache. This is the prefill phase. And it is really compute heavy. So here you would like to have hardware underneath that is made for that. And then the second phase is the decode phase, which is rather memory intensive or memory bandwidth intensive, and also latency sensitive. So this will read one token at a time from the KV cache and give you your output. So, like I said, these phases, different hardware needs. We are going to dive into that, like in, I don't know, 6 or 7 slides, a bit more. However, this is really a key insight for the entire talk, that these are 2 separate phases, and we can essentially split them up, which is also what the most advanced setups do. And I'm going to get to that also in a few slides for what we can do to optimize here further. But this is really core to the whole challenge of AI inference at scale. Now that we essentially have established the challenges, it would be interesting to know, okay, how does Kubernetes even see GPUs? Because that has changed in the past year, and it has gotten significantly better. Because what you would do in the past is you would have the GPU operator in your cluster. If you do not bake something like your drivers that will be exposed to the device plugin of Kubernetes, if you don't bake this into your images, you would have the GPU operator, which deploys drivers and the device plugin. The device plugin exposes information to the kubelet, and the kubelet exposes information to the scheduler. So far, so good. What's the challenge? So the challenge here is that with the device plugin, or with the combination of device plugin and kubelet, there is a thing in between called the topology manager, which originally was built for CPU and memories. So yeah, normal CPU and memory. There are some, let's say we made it work so that it also works with GPUs and other accelerators. However, it can only really allocate independent resources. But I'm kind of a hardware nerd. So who knows how GPUs and CPUs, memory, NUMA nodes, PCIe routes, how all of this works together at a hardware level? Okay, so it is kind of important actually to get like the most performance that you can get out of those expensive GPUs. So what you want to do is you actually want to align your GPUs in a way that you can say, hey, I want GPUs that are, for example, connected by NVLink in the same node. I want them to be on the same PCIe route as my network interface. I want them to be on the same NUMA node as my CPUs. So this is currently, let's say, you would have to do some gymnastics to do this with the device plugin and the kubelet. Also, this would be set for the node, so the whole node that you get, and it's not possible to set this per workload. So you couldn't go in and say, oh, I have, I don't know, GPT-OSS 120B running. For that, I want to have this configuration, and for, I don't know, Qwen 3.6, 27B, I want this different. It would be node-wide. Solution, since August of last year, we have DRA, Dynamic Resource Allocation. And together with specific drivers again, so DRA drivers, you can now define all of this stuff per workload. You can go and set per workload topology constraints, multi-device coordination. You can go and say, hey, I have so much money that I have like GB200 and NVL72 nodes running, which is like insanely expensive, and they have multi-node NVLink. You can now define all of this in Kubernetes using the common expression language, and this enables you to exactly define how you want your GPUs, or how you want to allocate your GPUs on a single node level. However, we want to go one step further, because now we understand, okay, how does Kubernetes see GPUs? And now to prepare for actually running inference, we have also we have to think about as well about how do we schedule pods and nodes? Because right now you might be doing it with just the Kubernetes scheduler, which is the default. But you need some more primitives if you want to go big. First of all, you want to have something like Q. The K is not a typo. This is actually the name of a tool. And normally, this would be used for in-cluster job queues, like the name probably says. But Q can do a lot more. So normally, you would use this for scheduling batch jobs and stuff like that. However, it has cool features like quota management, which you use if you have a big GPU cluster and you run not only inference on it but also training. You can then do preemption. So if the load of your inference workload rises, you can preempt, so you can kill the training jobs because those are lower priority than your, or probably lower priority than your customer-facing inference. It can do that. But more importantly, it has another feature called the queue populator. And this gives you internode topology awareness. So at a certain scale, if you have, let's say you really have hundreds of thousands of GPUs in use, you want to have the shortest distance between them physically, meaning you want to have GPUs which are sitting in the same rack at your provider. And the queue populator exposes this kind of information to Kubernetes so that you can then use nodes so that you can then use metadata in order to tell Kubernetes, hey, I want GPUs which are co-located in the same rack or maybe in the same group of racks. And on top of that, it gives you gang scheduling. Gang scheduling sounds weird, probably, but it is really useful, actually. Because normally, if you go ahead and say, OK, I want to scale up my deployment from, let's say, 10 to 20 replicas, maybe 4 will not be able to be scheduled right away. You will have to have another node spawning, and then the 4 pods will also be scheduled. With inference, you want to avoid that, because let's say you are scheduling a fresh inference workload. Let's say 5 out of 10 pods would be schedulable right away. If they start, and if it's a big model, and you have to actually shard the model over multiple pods, what will happen is 5 pods start, and maybe they will already be hit by traffic, but the model is not even loaded completely. So you will end up in some weird situation, and probably your users will hit errors. So what you want to have is either all pods get scheduled at the same time, or no pods get scheduled. And that is what gang scheduling does. And then you combine queue with the leader worker set. This is an extension of the workload API of Kubernetes. And essentially, this takes gang scheduling a bit further and allows you to really define multi-host inference groups where you can then go and essentially define groups and subgroups of pods so that you could say, oh, I want my prefill pods to have, 20 replicas and my decode pods to have 40 replicas because my workload is heavy on decode. And then you combine all of this with Carpenter, or at least something that goes in the direction of Carpenter. So Carpenter is an open source project, initially started by AWS. These days, it's part of the special interest group for autoscaling. And what it gives you is flexible scaling. So normally, you would scale your cluster with static node groups from probably your cloud provider, which are set on, for example, OK, it's only going to be, GPU node.x large, whatever, in size. Carpenter looks at what your pods actually need and then spawns the cheapest instance that can actually accommodate these needs. It also makes it easy to use spot instances, which gives you cost savings, and it scales to 0 automatically, which you can turn off, by the way. You might think now that, hey, you just told us that inference is a stateful workload. Why would we use spot instances? That sounds like a really bad idea, and it does. You are right. However, in a few slides, you are going to get the solution for that, because we are going to build the infrastructure in a way that enables spot usage for AI inference. Before we go into that, one last thing. You want to be able to squeeze as much power or as much utilization out of your GPUs as possible, because everything else would be literally burning money. And we don't want that, right? So how do we share GPUs for our workloads? Because not every model will need the whole GPU. Like, if you actually watch the space of open weight models right now, the Qwen models are kind of taking off, and the 27B version of Qwen 3.6 is it's amazingly good for the size that it has, but 27B won't really need a full GPU. So if you would want to run multiple of these small models, you want to share the GPUs. And you can do this in 3 ways. If you have the big pockets and you can run NVIDIA nodes, then you can look at MIG, which is multi-instance GPU. And this is hardware-level isolation. So this splits up your GPU in up to 7 instances with dedicated memory, dedicated compute, bless you. And yeah, I mean, this is super nice for production. I mean, honestly, the second one will also be nice for production, but this eliminates noisy neighbor problems. And if you have like a, let's say, very regulated workload, and your compliance people say, oh yeah, we need isolation of memory and compute, you want to look at this. The other version that I would recommend for production and or, for example, batch workloads is MPS, which is multi-process service. And this essentially does the same thing as MIG, it's just not hardware level, it's software level. So you might have noisy neighbor problems, there's no memory isolation, still you can essentially use this in prod as well. Then, last but not least, we have time slicing, and this is, I mean, essentially this hands out small time windows to workloads for when they may use the GPU. So there's a lot of context switching here, which probably has some performance implications. But it has simple setup. You can get really high density here, but I would rather use this for dev or test workloads. A bit of a side note, these are mutually exclusive. You can't use all of them mixed in over your GPUs, but you have to decide before, do you want to use either of those? You can't mix them. All right, so now we have essentially covered the whole hardware side, which is surprisingly relevant in 2026 for AI inference. And we covered how we schedule all our stuff. But now let's say you made it this far. So how do we now route our inference requests intelligently? Because let's say you have scheduled probably your VLM pods, because VLM has become the go-to standard. Would you now put a simple round-robin standard Kubernetes service in front of your VLM pods? Would you do this? I see someone who's not sure if he wants to do that. That's the right idea. You don't. You don't want to do a simple round-robin. Fair bit of warning. If you search this online, you will find out that most of the documentation calls it inference-aware scheduling, which means scheduling the request. I don't know how the industry converged on this wording, because I find it confusing, but hey, here we are. So how do you do inference-aware scheduling? This is the example implementation that I chose. This is what the LLMD project uses. If you look at AI Bricks and probably NVIDIA Dynamo has the same primitives, they all do this in some way or shape. The idea is you want to build an infrastructure that can accommodate this. And what I mean by this is your client hits your AI inference application, and the next thing that should happen is, so this box that says Envoy plus EPP is a inference gateway. This is a new API in Kubernetes, and EPP is essentially means endpoint picker. And this is essentially a, let's say, extension of the inference gateway, which is just Envoy, that LLMD has built. And what it does is, instead of doing round robin, it will have a 3-stage pipeline for your requests. And the first one does something really smart. It filters out overloaded pods, which is a good thing. But what is more interesting is it will then score your requests based on metrics, like, for example, cache hits. So in the last box is a KV cache indexer. So this essentially tells the inference gateway, would I have a cache hit if I route this request to port A, B, or C? And it looks at queue depth, but the most important thing that it does is it looks at session affinity. So it will know if, let's say, your user first asked your super awesome chatbot, what is AI inference? And now the user sends a follow-up request. The endpoint picker will know that, let's say, port 1 has served the request before, and if you would go with round robin, it might now happen that the next request gets sent to port 2, which will mean that it has to recompute all the KV cache because it doesn't have the context from before, which will introduce latency, it will waste compute, and we don't want that. So if you have session affinity here, the requests of the same user will get routed to the same ports in order to give them, in order to avoid recomputation of the KV cache and in order to avoid higher latency. So yeah, essentially I already said how it then selects, how it then routes to the best target. And the nice thing here is, so I would recommend this for every setup, no matter if you are really at scale or if you just do this for, let's say, 10 people in your office. Because what it gives you is, so LLMD ran a benchmark with Qwen 3 32B on, I mean, the 8 pods and 16 GPUs are more or less irrelevant, but 109% higher throughput versus round robin is, I would say, worth it. And 99% lower time to first token is also worth it, I would say. And the cool thing is, the configuration that they use, they are all open source. You can find them in their documentation /GitHub. So it's not like some secret sauce that they applied. It's all open, it's all out there. The next thing is something to squeeze even more performance out of your setup. However, I would not recommend this for every setup. So in the beginning, I told you that prefill and decode have different needs hardware-wise, and they are 2 separate phases. So what you could do is really split them up into separate pods and then scale them independently as well. And again, almost all the projects can do this these days. LLMD does it this way, that after the endpoint picker, essentially you send the traffic to a decode pod right away, which has a sidecar to organize the prefill with the prefill pod, and then transfer all the KV cache data via RDMA to the decode pod again. So we are back at hardware. But why would I not do this for every setup? So we, as in AWS, ran a benchmark on this as well, and I realize now that probably in the back you can't read any of this in the graph, but I'm going to tell you. So you might actually already know or think, hey, probably the line that shows better performance is most likely the split or the disaggregated prefill and decode, and you're right. So what you see here is we ran GPT 120B, so GPT OSS 120B, and we gave an increasing amount of concurrent requests to this model. And you can see that on the bottom left, at one user, this is like doesn't really matter. Actually, at this point, unified prefill decode is still faster. But at the second user, we already see an increase, and then the more the concurrency, so the more users you have, the more you will actually profit from this split prefill decode. You see a big gap at 32 users. For some reason, this is the point where it had the highest impact. But imagine doing this with, for us, GPUs are expensive as well, so we can't do this with thousands of GPUs either. But imagine you do this with thousands of users, or maybe even more than we went to up to 128, maybe even more than 128. So this is when it gets really interesting, and again gives you up to 70% of more tokens per second as concurrency grows. The cool thing is, LLMD even allows you, or this the endpoint picker even allows you to do this split prefill decode on a per request basis. So, for example, if only a small prompt comes in, you can route it directly to a unified pod. If a big prompt comes in, you can do split prefill decode in order to get some more efficiency out of this. Because here you can also think about, does this matter for my workload? Like, if you do a lot of RAG use cases, so if you, for example, have some system or you have a product for your end users that does stuff like chat with your document or chat with your documents, so you will have lots of big prompts. This use cases like these with a lot of RAG, these will profit from split prefill decode most likely. Still, keep in mind, if you do this for, let's say, the 8 users at your office, I probably wouldn't bother. But at the point where you go to, let's say, 32 users and higher, start looking into this. And this will go, or this will be even more interesting in the future. Because who has heard of any other AI accelerator than GPUs? So anything except for GPUs. TPUs, for example, exactly. If you run on Google, you can use their TPUs. But there's way more out there. So the AI accelerator space will accelerate, pun intended, in the future. So, for example, if you look at stuff like the Grok with a Q, not K, the Grok LPUs or the Cerebra's wafer scale engine, these are accelerators that are purpose-built, more or less, for AI workloads and for different phases of AI workloads. And they are going to get more available over the different cloud providers or the providers in general in the future. And this is when you can really get loads of more performance out of this. As an example, who is a Codex user or OpenAI user? 1, 2, 3. They are better than Claude. It's my opinion. But they, I think, somewhere at the beginning of this year, when we were at GPT 5.3, they announced a collaboration with Cerebras and subsequently brought out GPT 5.3 Spark. And this went up to over 2,000 tokens per second at their scale. You have to imagine the insane amounts of compute they need to have and the insane amount of optimization that this hardware is able to deliver. So in the background, this was the Cerebras wafer scale engine that enabled them to do this. So lots of this hardware is coming out. I would recommend you to really keep an eye on that, because this will give you not only more performance, but also most likely more cost efficiency. With that being said, we also talk a lot about the KV cache in this talk, or I talk about it, you listen. And there's another pattern that I want to tell you about that I would also recommend for most likely every setup. Because the KV cache is your most critical resource in all of this. Why is that the case? Normally, your KV cache is just your GPU memory, and probably that is not like an abundant resource, but rather a scarce resource. Your GPU memory is the fastest you have ever seen in your cluster, but also the most limited. So what do we do to get more memory? I mean, buy more GPUs, I guess, but no. We can actually do better and be a bit more cost efficient. So what we will do is we will do something very traditional. We will do tiering. And the second tier that we are going to use is pretty obvious, probably. It's DRAM. So there's a connector that enables you to offload some of your KV cache to DRAM. And what you can then do as well is offload even more to a shared file system. Yes, this should be really fast. So this, I mean, don't just go for whatever the fastest is that your provider has. Probably run some tests for yourself. But this tiering does multiple things, because not only does it give you more and also more reliable performance, which LMD also ran a benchmark on. And they did two things. They ran Llama 3.1 70B with 250 concurrent users, so simulated. And one of the setups had only GPU memory. The other setup had this 3-tier KV cache. And the 3-tier KV cache was able to sustain 185,000 tokens per second, while the GPU-only setup crashed to 13,000 tokens per second. So that's a 30.9x improvement from a setup that I would call, or from an idea that I would call rather simple. So this also is something that I would recommend to you to at least look at in your setup, in order to, I mean, not only get more performance, but rather reliable performance at scale when the requests to your application really go up. So if we tie this all together now, the inference stack essentially looks like this. Oh no. Sorry, I have to go one back. One important point that I almost forgot. The use of the shared file system also enables the use of spot instances. Because what you want to do, and I'm spoiling another slide, is this is going to be a read-write-many persistent volume claim. And new pods that, when you scale up in your system, new pods can immediately mount this and rehydrate and hydrate their KV cache from this shared file system and be faster available to serve requests. So if you have spot instances and they get removed and you have to spawn new instances, this is what enables you to do this in a more reliable way and maybe save a buck on expensive GPUs. Now we tie it all together to the inference stack. So at the very bottom, we have the shared file system and probably your private registry for your images. On top of that, we have Carpenter for autoscaling and your GPU nodes, which integrate with the DRA framework and the vendor drivers. Then we get the KV tiering on top of that. We have the VLLM pods, most likely for pre-fill decode, the inference gateway with the endpoint picker, and last but not least, your clients and the API. Before we all get lunch, a few more tips. I already spoiled this. Or also, I planned a bit for a Q&A in the end, if you have questions. Before we get lunch, how do we get weights to the GPU? I already spoiled it, but I see mistakes here repeatedly. So some people have thought about, hey, I'm just going to bake the model weights into my container image. Please don't. Please don't do that, because A, this will make your container image like huge, really huge. If you, let's say you want to bake DeepSeek V3 into a container image, you don't want to do this, because the pull will take enormous times, then the unpacking, don't. What you want to do is you want to put your model artifacts on an object store. This is your source of truth. Then you have a Kubernetes job that pre-populates your shared file system, and your shared file system gives your pods almost instant servability for your models. And as a shared file system, you can go with the with the classics like NFS or Lustre. If you have any, let's say, proprietary shared file system, use that as well if it gives you the right performance, whatever your provider gives you, right? Then, regarding the scaling again, you don't want to scale on the same metrics as you would do with a web application. You want to look at metrics that are relevant for your GPUs. And of course, you want to have two-layer autoscaling. So on the one hand, you have the HPA, so the horizontal pod autoscaler, as well as if you use the leader worker set, it also gives you the WVA, the workload variant autoscaler, which is essentially it gives you the ability to define different model variants and scale them differently. And then on the node level, of course, you have Carpenter. In the end, there are 4 metrics that are actually interesting. First one, time to first token. Your primary latency indicator. If you see this climbing, you most likely have a prefill bottleneck that you want to look into, or cache misses, to be honest. Then you have time per output token. This is your generation speed. If this spikes, your decode is most likely contended. KV cache utilization. You want to keep this close to 90. Don't go above 90. If you go above 90, you will have massive performance degradation. You don't want to have that. And queue depth, so how many requests are in your queue. This is your leading indicator as well for latency. Last but not least, 5 things you want to remember. First of all, make GPUs a first-class resource in your cluster. Second, you want to really double down on this prefill decode split. You want to understand that these are 2 dedicated phases. 3, your KV cache is your most critical resource, even more critical than GPUs. 4, do not autoscale on the web application metrics. And 5, due to that, invest in observability early. That being said, it is April, end of April right now. Maybe in like 2 months, all of what I said is rubbish because of this ecosystem moving so insanely fast. There's a lot more stuff out there that I couldn't cover today. So with that being said, thank you for coming out here on a Saturday. Thank you for listening to me. If you ever want to buy anything on Amazon, scan this QR code. No, it's my LinkedIn. Happy to connect with you. If you have questions, I mean, it's 2 minutes until lunch. I don't want to keep you, but just approach me. I'm here until 1, then it's time for me to go home. Yeah, thanks, Devoxx, for inviting me again.
Thank you very much, Alex.